Find the minimum cost. In this problem, a reservoir begins with 14 units of water at the beginning of the first time period and ends with 0 units of water at the end of the third time period. There is no inflow into the reservoir. The objective is to minimize the cost, which equals the flow to the city, CI squared, summed up for each time period, I. The flow to the city is a function of the reservoir release for each time period. In the first time period, only 1/3 of the reservoir release flows to the city, and the remaining flow is diverted. During the second time period, half the release flows to the city, and in the third time period, the entire reservoir release flows to the city. In this problem, the volume of water in the reservoir is the state variable, and the release of water is the decision variable. The volume of water in the reservoir after the first stage, V2, equals V1 minus X1. Similarly, we can write out V3 and V4 by subtracting the previous release from the previous volume. Since we were given the final volume equals 0, we know the third and final release must equal the volume of water in the reservoir at the beginning of the third period. Decision variables x1 and x2 can be written out in the same way. In dynamic programming, the left set of equations represents the non-inverted form of the state dynamics equations, and the right set of equations represents the inverted form of the state dynamics equations. The final and initial reservoir volumes are considered boundary conditions. For this problem, we'll use the backward pulling algorithm, where the optimal objective function value, capital Fi, for a given state, Vi, equals the cost for the current stage, Ci squared, plus the cost for all previously evaluated stages. For I equals 3, we know the flow to the city, C3, equals the release from the reservoir, X3. Since the final volume equals 0, there is no cost associated with the final state, V4. From our state dynamics equations, we know X3 equals V3, which means the optimal objective function value for V3 equals the volume of water in the reservoir at the beginning of stage V3 squared. For stage 2, only half the reservoir release flows to the city. Also, we can plug in the future optimal objective function V3 squared. From our state dynamics equations, V3 equals V2 minus X2. After substituting this value and simplifying the equation, we'll next set the derivative with respect to the decision variable x2 equal to 0 and calculate x2 equals 0.8 times V2. To find the optimal objective function value at state V2, we can substitute in for variable x2 and remove the minimum note because we've already found the value of x2, which minimizes the objective function for this state. The optimal objective function value at state V2 equals 0.2 times V2 squared. In stage 1, we'll again plug in the cost function and future cost calculated from stage 2. Next, we'll replace V2 with V1 minus X1 from the state dynamics equation and write out the entire equation. Next, we'll differentiate with respect to X1, set the value equal to 0, and compute the release in the first stage, X1 equals 9/14 of the initial reservoir volume. If we substitute in this value for X1, the optimal objective function value at stage 1 equals 1/14 times the initial volume of the reservoir squared. Plugging in the given initial volume of 14 for V1, the minimum cost equals 14. When reviewing the possible solutions, the answer is A. To find the optimal releases X1, X2, and X3, which will achieve this minimum cost, we can recall equations we already computed for the release as a function of the volume at the beginning of each stage. Knowing the initial volume is 14 units of water, the release during the first period is 9 units of water. The volume at the beginning of stage 2 equals 14 units minus 9 units, or 5 units, which makes the release during stage 2 equal to 4 units of water. This leaves only 1 unit of water in the reservoir, which is released during the third and final stage.